Hello, so in this video we will talk about Markov and Chebyshev inequalities. So let's start with the definition of both of them. So if we have a random variable x which is defined in the sample space S and it has a mean of uh, mu and a variance of uh, sigma squared, then the Markov inequality says that if we have a positive real number a, then the probability of x being greater than or equal to that number a is always upper bounded by mu over a. By upper bounded we mean that it's always less than that number. Okay, okay. So let's see how does the proof work. So this is our proof here. So we start with our right hand side. So this is our mu over a. So what is the definition of mu? The definition of mu is I times the probability of x equals I and divided by a, and we sum over all the values in the sample space. Okay, so then this is always greater than, if we impose another condition on I, that I should always be greater than or equal to a, then this is obviously we are not changing the argument in the summation, we are only changing the limits of summation. Now we are summing over less number of terms. If we are summing over less number of terms, then I greater than a only constitute a subset of our sample space. So then this guy, this summation is always less than or equal to this summation. Now this guy, this I over a, now we are talking about the case where I is greater than a. So if I is greater than a and a is always positive, then I over a is greater than 1 or less than 1. So I over a, so we are saying I greater than a. So this means I over a, this is greater than 1, correct? So if this guy is greater than 1 and I am replacing this I over a by this 1 here, so in that case I over a is greater than 1, so then this summation here, whatever I multiplied by I over a is greater than 1 times whatever I have multiplied by I over a. So this means if I replace I over a by 1, then this summation will be, this guy will be greater than this guy. Okay, so what is this guy? Now this guy is nothing more than our probability that x is greater than a, correct? So then what did we do? We started with mu over a and then we proved that this is always greater than or equal to probability of x greater than a. So then we have proved our Markov inequality. Okay, now let's move to the Chebyshev inequality. Okay, so for Chebyshev inequality, what do we do? What do we need? Okay, and this whole line is my set S. Okay, now let's start. Now we are here, we are saying that probability of x not equal to a, this is equal to the summation of all I which are not equal to a, and we sum the probabilities here. Okay, now we consider our I minus mu over r. Okay, now I want you to consider I minus mu over r in this range. Now note that if this is a, we are, and considering I not equal to a, so we are either here or we are either here. Okay, in this range the distance between I and mu is greater than r or less than r. It's greater than r because the distance at r are marked by mu plus r and mu minus r. So in this range my I minus mu is always greater than r. I mean absolute wise, right? Absolute distance wise, I minus mu is always greater than r, or in other words, the distance of I to mu is always greater than the distance of mu to mu minus r or mu plus r. In other words, this I minus mu over r is always greater than 1. This makes sense? So then this means that this guy is always greater than this guy because this guy is always greater than 1. Okay. Now now what about this guy? Now here in this summation, in this one, we are considering only the part where we have I is not equal to, I is not in A. But here we are considering the whole sample space. Now if we are considering the whole sample space, this summation has to be greater than the previous one. Why? because we are taking the square here, and these squares are always positive terms. So we are adding more positive terms to this summation to get to this summation. So that is why this summation is always more than this summation. Okay, and this is nothing but, we can take r square outside, and then we have I minus mu squared probability of x is equal to I, which is nothing but the variance. Okay, so whatever we have, the argument is, we have in the summation is this guy, so 1 over r squared times the variance of x. Now we started with probability of x not equal to a, and we proved that this is less than or equal to sigma squared x, which means the variance of x divided by r squared. So this is the so-called Chebyshev inequality. Now let's see a small example to demonstrate the application of these two. Now let's say we have a factory which produces items with a mean of 10,000 items a day. So 10,000 items a day, and with a variance of 1,000 items. Okay, now we are interested in what is the probability of manufacturing 11,000 items or more items, 11,000 or more for any given day. So we are interested in probability of x greater than 11,000. So we can use the Markov inequality, and we know that this will give me mu over a, and what is my a? This is my a here. So then we will say mu over a, so this is equal to 10,000 over 11,000, which is equal to 10 over 11. So this means the probability that on any given day I will produce more than 11,000 items cannot ever exceed 10 over 11. Okay, 10 over 11. Now note that in Markov inequality, one of the conditions we need is that this x should always have positive values. So in other words, I cannot produce negative 500 items. So this Markov inequality is always applicable whenever we have the random variable cannot take negative values, right? Okay. Now we are interested in what is the probability that the number of produced items are between the 900 and 11,000. Okay, so for 900 and 11,000, if we go back to our Chebyshev inequality, then we have a mean of 10,000. So this is the mean, this is 11,000, and this is 9,000. Okay, so then this means my R is equal to 1,000, because the distance between the mean and the two limits is 1,000. Okay, so what is the probability that x is not in a, which is upper bounded by sigma squared over r squared, which is 10 to the minus 3 here. So if this is upper bounded by 10 to the minus 3, then the actual probability that I am in a is lower bounded by 1 minus that number. Okay, so in other words, if the probability of x not in a is always less than or equal to 10 to the minus 3, then the probability of x in a is always greater than or equal to 1 minus 10 to the minus 3, which is 0.999. Okay, so this is the application of Chebyshev inequality, and this is the application of the Markov inequality. Markov inequality and Chebyshev inequality both gives upper and lower bounds to different kind of ranges. So for Markov inequality, we can find a probability greater than any number if the random variable is positive. Okay, always positive. So here we have to be extra careful here. For Chebyshev inequality, we can say how far the random variable is from the mean, and that depends on the variance. Okay, so specifically this is the formula, and then we have seen how to apply it in an example here. So hope it was easy to understand. Hope you like the video.